So maybe while people are still joining, maybe we can start. So hello everyone, and Happy New Year, and hope you all had a nice break. And this year we're getting closer to the end of the pandemic. So as the first speaker for this year, we have the pleasure to have Peter Battaglia, who is a research scientist at DeepMind, leading some of the activities in the domain of GraphML. Previously, he was a postdoc and a research scientist in MIT's Department of Brain and Cognitive Science. His current work focuses on approaches for reasoning about and interacting with complex systems by combining richly structured knowledge with flexible learning algorithms. So thanks a lot, Pete, for taking the time, and it's a pleasure to have you here today.
Okay, thanks. Okay, so you can see me and hear me, right?
Yeah, you can.
Okay, great. All right, yeah, so thanks a lot. I'm going to try to, I put probably more material in this talk than I necessarily need to present or have time to present, but we'll see how it goes, and then I might leave some time for questions at the end. But feel free to sort of jump in, I guess, with short questions if that's the kind of normal thing that's done here. Okay, thanks. Yeah, so my talk is titled Modeling Physical Structure and Dynamics Using Graph-Based Machine Learning. So the first sort of point I want to make is that when we as data scientists, as machine learning researchers, when we look around, many important domains and problems are richly structured. So these are some examples. I'll sort of let you glance around at the slide for a minute. You can see there's sort of tree structure, graph structure, other types of interesting structure. So when we're faced with some problem, we often ask, what tool do I need? So if our data is sort of vectors, we might pull out a multi-layer perceptron neural network these days. If it's grids, we might dig into our deep learning toolkit and use our convolutional neural network. If it's sequences, maybe it's a recurrent neural network, or transformers, I think, are often used these days for sequences, but also other things. If your data is structured, I think what you want to be thinking is, I'm going to use a graph neural network or a transformer style architecture, and I'll sort of describe now what these things are. First, I just want to sort of outline the purpose of the talk. So the purpose here is I want to show you some of how my group has applied these graph-based machine learning methods like graph neural networks to richly structured objects in physical problem settings. And throughout the talk, hopefully I can kind of help build some intuition for how we approach these problems and how you can apply these methods to other sorts of structured problems. Because I think we often find that a lot of the methods that we've been working with and developing can transfer sort of quite nicely and neatly to other regimes. And then also, just as a small point, a lot of the work that I'll present, we've open sourced the code. We've also open sourced some graph neural network libraries for JAX and TensorFlow. So I'll just sort of highlight those at the end in case you're interested in playing around with some of this stuff. Okay, so as a quick background on graph neural networks, what we've been doing in my group is we've been developing and working with a class of models we call graph networks, which is basically a general formulation of graph neural networks. So graph neural networks have been around for about 16, 17 years now, and have sort of rapidly grown in popularity, I would say, in the last maybe 6 years. And there's a lot of different models out there now. There's also a lot of other deep learning architectures which are sort of related to graph neural networks in various ways. And so some of what we want to do is try to unify this and make sense of this sort of ecosystem and this different kind of taxonomy of architectures. We designed this, what we call this graph network formalism, to be both expressive but also easy to kind of implement and use. And generally, what you want to do is you want to think about it as a graph-to-graph function approximator. So it takes a graph as input, and it returns a graph with the same structure as output, but it predicts different attributes on the edges, nodes, and/or at the sort of global graph level. So let me describe sort of how this kind of complicated box works. So if you have some graph, so that's in the top left of the screen, you've got your nodes as represented by V, your edge attributes by E, and then that U diamond thing is supposed to be like a sort of graph level feature as well. So the way that this algorithm works is it takes as input the graph, so it takes as input the edge, node, and global level attributes. And again, it predicts some update to them. The first thing that happens is it applies a neural network function, which you can see. Actually, I don't know if I have a pointer. Let's see if I can get a pointer tool so you can actually see. I don't know if this is going to work. It's too bad. Okay. Well, can you actually see my mouse or my cursor or no? You can. Okay. So this phi e is a function, and typically it's a neural network, and it's going to take as input one edge attribute, two vertex attributes, and the global feature. And it's like sort of captured by this blue oval here. It's taking the two nodes that are connected by an edge, okay, and it's going to return an update for that edge. And that's sort of like sweeps this function all over the graph in parallel over all the edges. And then for all the edges, it computes some E prime K. So some update, some per edge message or update. Then what happens is it applies a second function, this phi v, to each node. And the phi v is going to basically take all the messages or edge level predictions that are corresponding to some node and update the node in the context of that node's sort of input state and also all the messages of what its neighbor is saying. So it kind of sweeps this phi v function all over all the nodes of the graph as well, and in parallel, and then it predicts a v prime I over here. So it updates for each of the vertices or node attributes. And that's like the node block, okay? It also, the reason I have this E bar here inside the argument is just to signify that it's pooled up all the information from the edges. It doesn't have to be a summation, it could be something else as well, but so it's taking all the information about the edges that are incident on the ith node and then giving that to the node's update. And finally, another option, this is sort of an optional step usually, but sometimes we use it, sometimes we don't. It's good for outputs often. Is you have a global block. So you run your graph network, you take all of the, you take that global level input feature and also the aggregated node and edge level features, and then predict something about the whole graph, like some new, attribute for the graph. And this formalism is sort of very general. So in the center, you've got the kind of, what I just described, and you can see the phi e, the phi v, and the phi u, and these rows are these like summations or aggregation things I mentioned. And if you look around the sort of periphery, you see a bunch of other classes of models that all, if you kind of squint your eyes, they're just sort of like cookie cutouts of this central block. So this sort of central thing is kind of like a general framework. And if you start to just like remove parts of it, you get other things. You can get like message passing neural networks or interaction networks or graph convolutional networks in the top left corner. Deep sets is a model that's applied to sets. It doesn't have any notion of edges or relations, so it sort of doesn't have that whole pipeline on the bottom. We published several years ago this relation network. This is sort of a very simplified version of this. Or also even transformers or other non-local neural networks can be viewed as special cases of a sort of general graph network architecture. You can, like, when you're sort of doing your deep learning hacking, you can like compose graph network blocks together, just like you can compose convolutional neural network blocks together into different arrangements. So you can have sort of like a deep graph net. That's kind of the top left here. The bottom left is sort of like a shared GraphNet core. We have the same sort of parameterization of this core that's being repeatedly applied to this graph. You can get kind of fancier architecture. You'll see this a lot, this encode process decode architecture we use, where you have some graph network that's encoding some input graph into some latent representation, and then usually a repeated or an unshared, either shared or unshared sequence of blocks of graph network, and then a final decoding out into whatever the output space is. People also do like recurrent graph networks and things like this. So you can kind of play again the same kind of plugging these blocks together in your favorite sort of deep learning library. Okay, so that's how they work. So the first thing I'm going to do now is start to get into the actual kind of like research part of the talk, where I talk about how we've taken some problems that we think are very interesting and then like sort of applied these graph neural networks or sort of related methods to trying to solve them. So a lot of what my group does is we work on learning simulation. And so for several years, we've been sort of building up a kind of increasingly more, I guess, like fancy, sophisticated sort of techniques for simulating complex systems. So this is work that was published in ICML last year, I guess 2 years ago now, it's 2020, where the idea is you have a physical system that's represented as a set of particles. So on the top left, you've got like this three-dimensional box that's got this, it starts with this cube of fluid particles, but then as you can kind of see, if you look at the sequence of frames, you've got the particles that are sort of dropping and like splashing. They have this sort of splashing behavior. And you saw that in the first slide of the talk too. I have a video of it if it wasn't too choppy. And the idea is what we want to do is, so this is like, this was produced by an actual particle fluid, like a particle fluid simulator, but we want to train a neural network to simulate this system and see if we can, instead of using an engineer's simulator that somebody's built by sort of trying to numerically approximate the equations of motion of this fluid, we want to see if we can take observed trajectories of the state of the system and then train a model to act as a simulator, just like the underlying simulator. And the reason we do this is because we think that there's a variety of reasons of why you would want to learn a simulator. One is because simulators are very expensive usually. So often to get good accuracy, you need very fine spatial and temporal resolution. So one of the things that we've been exploring, and I'll talk about this more in a few slides, is how we can take like a high resolution, expensive simulator, generate data from it, and then use it to train a model that's much faster. And the hope is that we can kind of get like, a better speed accuracy trade-off. And this is especially important when you're just trying to solve like inverse problems where you want to run the simulator forward many times to search some space of like either inputs or parameters that hidden parameters that you're trying to fit. Another reason is, we're starting to just do this now. I'm not going to talk about this today, but we have some sort of more recent work. It's ideally we would start to learn simulators not from data that was generated by an existing simulator, but from actual observations of nature, where we actually just take, so I guess in the sort of work that we're about to sort of publish and release, we've been taking like solar system data, so trajectories of the planets in our solar system, moons and planets, and actually just fitting learned simulators to that data directly rather than actually even needing a simulator. And the hope is that we can do this with like, again, increasingly sophisticated things that don't have good simulators for them. Anyway, so here's how this works. So if we're going to simulate this system or train some simulator, we have our learned simulator that's going to be designated by S theta. It's comprised of two components. An update mechanism, which basically just sort of says, well, actually, let me start from the beginning. The D, which is supposed to indicate the dynamics, some kind of dynamics prediction, and that's parameterized by theta. So it's like it's making some prediction about how the system is going to change over this time step. And then the update is usually just some fixed mechanism, just like an Euler integrator or something simple that just takes that whatever that dynamics information is and just updates given the past state to evolve it into the future state. And this is supposed to be sort of a general kind of framework, like we're going to plug in different components for these things. But the reason we kind of separate the two things is because the D theta, which is parameterized, is like going to be represented by a trainable neural network. So here's this encode process decode sort of scheme that I described a few minutes ago. If X represents the input state of the particles, the encoder transforms the X, Y, Z positions and velocities into some high dimensional per node vector. So on the bottom left here, you see like the blue represent the particle positions. The encoder, it projects the particles and into some high dimensional representation. It also builds us a graph based on the local neighborhoods. So any particle, that gray circle is meant to indicate a local neighborhood around that sort of darker gray sphere. And you can see there's dark edges that connect that center dark sphere to its neighbors around it. We do that for all the nodes. And then you build up a little nearest neighbor graph. And the input, the input X positions are run through a neural network. It's like an encoder that produces some latent vertex attribute. And we also take the displacement vectors between the nodes and project that into some high dimensional representation, that's the edge attribute. Then the processor passes messages between the nodes in this fluid graph. So basically, you can see like the lowercase m is meant to represent the how many which processing step you're on. So if you have a sequence of processing steps, you're going to just like keep iteratively updating the vertex and edge attributes, and then sort of allow the information from different parts of the physical system to propagate across and kind of inform, nearby parts. At the end of that processing pipeline, you have like an output graph, latent graph GM that's then decoded into some output prediction Y. And here Y is just representing the displacement vectors of the particles. So it's just if this particle started here, and then in the next time step, it should go over here. And the prediction of where it goes depends, physically depends on this little neighborhood of particles, and the neural network is supposed to figure out how those dynamics work. Okay. And so when we do that, this is what we get. So on the left of this video, you got your round truth simulation from the actual simulator that it was trained on. And on the right, you've got some held out test data. I should say one thing. We always train these models on to make one-step prediction. The model only takes one step and just predicts the next step. To generate a sequence of trajectories, we just take its own prediction and feed it back into itself, like to make a rollout, I'll call them. So, and so here, the reason it kind of looks like a continuous fluid is just because that's like a post-processing step in this 3D software. You're going to see in a second, it's going to kind of convert sort of smoothly into its particle representations. So here you've got this is the actual underlying particle representation of this fluid. So on the right is a full neural. All we've done is given it that initial cube of fluid, and then started making predictions, and then feeding its predictions back into itself and generating this rollout. And you can see it's like quite accurate and sort of compelling as a fluid. We can do this with other materials, so we can simulate things like sand-like materials, and this works. I'll kind of skip forward to the particle representation again. And this other material, which I think the technical term for it is Goop. It's just sort of another kind of highly viscous kind of fluid that really doesn't flow very much at all. Here's its particle representation. Here's it. I can't get the particle representation. Where is it? Yeah, there's the particle representation again. And these are also generated by different simulators. So I think the first one this one was SPH, smooth particle hydrodynamics, and these other ones were this completely different simulation and completely different technology, like material point methods. Because both the simulators operate on particle-based representations. This makes them applicable to our method, to using our method to try to train. And yeah, you can see in the top there's about 19,000 particles in this example. So it runs a pretty good scale. Here's another example. We did a lot of 2D examples because it's sort of easier to make complex kind of interactions and obstacles and stuff in 3D. It's sort of it's kind of hard to get interesting stuff to happen. But you can see it can interact with rigid sort of walls and obstacles. We can also have multiple materials that are interacting with each other. And this is actually an example. Oh, it's even choppy on my screen, so it's definitely choppy on yours. No, maybe, I'm not sure if the video is broken or something, but anyway. So you can see you've got this sort of water, sand, and goop all interacting in the same box with each other. So here we actually train. This is an example of generalization too. We train on much smaller boxes with much simpler interactions, and then at test time we just made the boxes much larger. The reason we can do this is given by the way I described graph neural networks at the beginning, which is the functions are only operating at the sort of local interaction level, it's pairs of particles or it's individual particles that are being updated. These models don't know anything about the whole system. They're basically just making local predictions over the graph, kind of how a ConvNet makes local parallel predictions about the regions of the image. So when you train on small graphs, it's often quite easy to, these models often generalize quite well to much larger graphs. And we can even simulate sort of rigid materials. So this green is this, it's like a cube made out of rigid particles and it's floating around in some fluid. We just give as input to the model, we basically annotate the different particles with their material types. So the green ones have a little integer feature that represents solid, and the blue particles have a input feature that represents liquid. And all we have to do is just tell the model this is going to be a solid, this is going to be a liquid, and then it can sort of like figure out that their behavior has to be different. So the greens can't have to kind of maintain the same relative relationship with respect to each other. Cool. So we've also done this more recently. This slide needs to be updated, actually. So this was published in iClear 2021, sort of like about a little less than a year ago. Yeah, so we've not only have we done the similar, like used these types of models with particle-based systems, but also we have sort of extended them to mesh-based systems. So that in this work, the physical systems we explored are the ones in the slide. So the cloth on the left is, let's see if I can, oops, I'll try to play that in video again. Yeah. So the cloth on the left, you can see is sort of like represented by a mesh. You can, if you look closely, you can see there's a little like kind of spider web of kind of vertices and edges that represent this cloth. We also have a structural mechanics data set that we built where this is simulated by ComSol, which is like a structural mechanics sort of software simulation tool. We also have compressible and incompressible fluids. So like compressible fluids are like air around the wing, and then on the right you have like incompressible fluids are like water or liquid. This is like a very sort of like standard domain called cylinder flow that lots of sort of simulation tools are evaluating. The model works quite similarly. So you can see again, you got your update mechanism in the middle here. The D, or like the dynamics predictor, is also here. That's what this like chain of 3 steps down in the sort of middle bottom of the slide are. Again, you just encode the input into some graph and then run your processor several steps, like a number of times, and then run your decoder to decode it back out. The differences are now we've got 2 different kinds of edges in this graph. So one kind of edge is the types of edges I described before, these like kind of contact edges, like particle, vertices that are near to each other in space. They're instantiated with a little neighborhood graph, and that's represented by the red edges in the bottom graph. You can see like it's the sort of, the ball as it makes contact with the cloth, it sort of has these red edges that are instantiated and used to sort of allow the communication that reflects the rigid interaction between the cloth and the solid ball. You also have the second type of edge, which is the mesh space edge. Because these are actual, these are solid, non-rigid materials, they have to like maintain, like the cloth has edges. So just because 2 vertices are, if you fold the cloth, it's not that like the cloth, when it folds onto itself, it starts to stick. It's the cloth is, its shape is defined by neighbors which are fixed over time. So the neighbors in the cloth are always going to be its neighbors in its cloth. So you need the mesh space edges to reflect that. And this is how normal sort of all mesh-based finite element method simulators work. And we have 2 different functions. So mesh space edges, world space, we have 2 different functions used to compute each of these types of edges. So really all we've done is we've sort of taken from the previous thing with the particles, we've just taken like a second one of those and just layered it in parallel, where now it's predicting the mesh space edges and you got the particle one as well. And then those predictions are just being concatenated together and like used to inform each other at every step. One thing that was very interesting about this is we had temporarily, we downsampled the simulated data so that we were training to make much larger, longer predictions than the simulator was making. And in general, this would give us sort of like about a 10 to 100 fold speed up in over the actual simulator on which it was trained. So now this is where we're starting to kind of like see that we actually can use, insofar as our simulated model, our learned simulator is accurate, or is accurate enough, we can, sort of look for good speed accuracy trade-offs, because if we're sort of like near similar accuracy to the underlying simulator, but like orders of magnitude faster, that's something that we're kind of, interested in. Okay, so here's some of these results. So on the left, again, you've got your ground truth cloth, and on the right, you've got your predicted cloth. Same setup, you just have the initial frame is given as input, initial state. It's given to the simulator, it makes a prediction, it feeds it back into itself, it continues to make a rollout for 1,000 steps or more. The reason it says learned remeshing here, we also had some extra sort of bells and whistles here. Most of these simulation engines, the engineered ones, they have like fancy sort of adaptive mesh refinement, different kinds of remeshing strategies, because as the dynamics of the dynamics unfold, different parts of the system need more or less resolution. So if you were to slow down these videos and look closely at the ground truth, you'd actually see that the mesh is changing on each step. So rather than just so we needed a way of basically, so one thing we could have done was just keep because remember, we only want to take the input of the system. So we could have just maintained that input graph, but we know that that's not such a good idea. So what we do is we actually train a second model that predicts how the mesh will change, basically, like how the underlying simulation engine will remesh. We make a prediction of that, and then we use that to remesh. So the idea is we can also adaptively remesh our system according to the same principles the ground truth simulator used in order to get more accurate simulation. And we do, I'm not going to show that here, but you can actually see when you compare them that it does help. And this is why they use them in real engines. Here's the structural mechanics. It's almost indistinguishable from the ground truth. In this stuff, I'm not even going to show like sort of numbers and stuff. We're not, I'll be honest, we're not entirely sure how to measure accuracy because there's different ways to measure. So one thing you could do is just say, how accurate is your simulator on one-step prediction? Like how close, in mean squared error do you get? You could also say how accurate is it over like 1,000 time steps or whatever. But it starts to, that's not always what you care about, especially when things start to, like some systems that are chaotic can be very sensitive to initial conditions. So you might still get a very, very accurate simulation in the sense that the only errors are just like it can diverge wildly, but only because it made a very small error somewhere along the way that just manifested in kind of like, so for example, if you drop a ball on like a triangle, if you just kind of slide the ball left or right, it might go to the left or to the right, but like it was pretty accurate, even though the error over a long period of time is going to be very, very high. So this is a sort of open problem that we're sort of trying to figure out, and it's not clear to us that there's a really great way to do this, but typically, I think it's more like thinking about what the downstream problem is and then just how well does the simulator support it. So here's the compressible and incompressible fluids. Here, nothing is moving. What's changing here is like the pressure and the flow fields and stuff. So basically, the mesh, like it's not like a cloth that's moving around in space. It's just again the sort of where there's the pressure and the velocities are changing, and that's determining like where the kind of liquid is going. Again, we do all sorts of generalization experiments. So here we've trained on a smaller kind of cloth that's shown in the top left corner, and then we at test time we just built other kinds of meshes like this sort of fish banner windsock things. And over on the right, you can see it's a much, much larger system. So in the bottom, in like the right video on the bottom left, you see the training cloth. That's how big it was to scale. And then you can see it's like generalizing to a much larger system with like kind of complex sort of like weird tails at the edge of the windsock and stuff. So again, there's sort of hope here that by training on small, high resolution information, data from real simulators, that we can maybe simulate more generally across more complex and systems that like people might care about. But they didn't know they cared about it when they were training their model, but they can still run the simulator. Okay, so that sort of wraps up the part on physical simulation. Let's see how am I doing on time. Okay, yeah, I'm good. And again, the whole sort of point of this part of the talk was to show that like you can take these physical systems and represent particles and meshes, and you can represent them as a graph. I mean, a mesh is a graph already, but like you can represent it as a graph that can be processed by a graph neural network, and this graph neural network, can be trained by supervised learning to, behave, to get pretty accurate sort of prediction with respect to the underlying, simulator data that you're interested in. Okay, so another thing that my group has been doing, so we're in general very interested in like three-dimensional sort of, we like things that sort of look good on videos and, animated GIFs, I guess, but like, 3D objects, 3D simulations with sort of rich dynamics. So this is a project by Charlie Nash, and it's called, he called the system Polygem. And what this is an autoregressive generative model of 3D meshes. So these two things that you're seeing were generated by, oh, sorry, no, actually not these two things. I'll show the things that were generated in a second. These are real data. So we have a data set of 3D meshes, like that contain things like chairs and dressers and lamps and other stuff like that. And the way those 3D meshes are represented is in their, in the computer, in the code is, or like in the, the file in the computer is an OBJ file, which is a very common 3D object file format. And it's very simple. It's like this is the OBJ file for that cube on the bottom right. If you look closely, basically the top, every OBJ file has like at least two parts. It has a vertex. The first part of the file is just labeled with these V's for vertex. That's like where all the corners are. So because this is a cube, you'll notice there's 8 lines here. And if you look closely at these coordinates, they actually do form the corners of the cube here. Then every OBJ file has a second like sort of part, which is the face list. And what that is a set of indices of the vertices which are connected by edges and form a face. So this top face, let's see, we can even probably do it. So 0, 2, 2 would be like, x equals 0, 2, 2 is, up and back. So that's going to be like probably the, like this face, like the left side of the cube and like probably this corner over here. And the second vertex is going to be the bottom over here. And the third is going to be, let's see, probably that one and there. You can see my cursor, and the fourth one is going to be this one. So this first face, 1, 2, 3, 4, for these first 4 vertices corresponds to the back face of this cube. And if you just look closely, these are the indices that, like this is, each face on a cube has 4 corners because they're squares, and so each face has 4 indices of the vertices. So this is just indicating which of the vertices comprise each of the faces. It's just a list of faces, face list. That's a cube. So this is how an OBJ file represents it. So like we kind of like tried to keep it sort of simple. So all we did was like, well, why don't we train a model of this vertex list, and then after we train that model, we'll give that vertex list that it generates to another model that'll generate a face list, and then that will see if that thing can learn to predict cubes or any other shapes that are represented by OBJ files. So a generative model of a 3D mesh, what you want is to run the model and it spits out representations of the 3D mesh sort of without any kind of inputs, like an unsupervised, or just an unconditioned rather generative model would just generate arbitrary meshes that are like realistic, the kinds of meshes you would find in like a data set of 3D object meshes that we trained it on. So here's how it works. So it's transformer based. So I didn't explain how transformers work. You can kind of think about them as graph neural networks, but instead of taking an input graph where the edges are like kind of sparse or made explicit, it assumes there's edges between all the input, a set of input points. It assumes they're like fully connected. There's edges between all of them. And it uses, a transformer is distinguished by inside it uses a mechanism of self-attention, it's called. So it's computing weights, little gate values or weights between all the input set of particles or nodes, and then sort of doing a weighted sum of them. So like it's sort of almost like the way I think about transformers is they're basically just learning an implicit graph, a kind of soft graph about the interactions between all the elements. But you don't really need to know that much. You just need to know it's sort of similar to a graph neural network. And people have heard about transformers a lot in sequence modeling and language modeling. The implied input graph is like all of the previous words in the sentence are connected by edges to the future words. So that's how they use that. They make word level predictions by assuming all the previous words in the sentence are fully connected, and they're going to predict the new word. Okay, but we didn't use this on words or text. We use this on 3D meshes. So how do we do this? So the first thing is we just predicted all the vertices, all the little corners and nodes in the mesh graph. I won't get into the details, but basically what we do is we start by just predicting one vertex location, and then we condition the transformer model on that vertex location and predict the next vertex location. And we just keep iteratively predicting the next vertex location by conditioning on the previous vertex locations. And there's a whole bunch of like sort of details that I'm skipping over, but it's not that important. This is the sort of general idea. You can check out Charlie's paper if you want to know details. His code is also online. I'll have a link to that at the end, which I'll share. So on the left, you got this sort of schematic that demonstrates this. You can see the conditioning is conditioning on all the vertices it's generated so far, and it's then predicting it predicts actually one by one z, y, x coordinates of the next vertex. And it just does that like thousands of times for all the corners of, all the coordinates of all the vertices in the mesh. When it's done generating a sequence of vertices, so that, again, that's this first part of the file. So basically, the way to think about this is really, in many ways, is sort of a language model just applied to this weird file that's not actually like natural language. We just like run it over these coordinates like this, and it just is doing, just like you have, your GPT-3 generating words in English. Here we're generating vertices in meshes. Then we do something that's slightly different than what's done. So we use a transformer again, but now what we have to do is we're not predicting the number. We're like referring to which. So to predict the faces, we need to refer to which vertices should be part of each face. So what happens is we basically condition on all the vertices that have been generated and start generating not like numbers, but sort of pointers to the vertices. So we basically have the vertex list and we highlight which ones should be connected to each other. So we like predict the score of which is the next vertex, which is the next vertex in this list, which should be connected in the face that I'm building. And you can see that in this plot. So basically what you're seeing is in the cube, it's like building up that front face corner by corner. It's like vertex here, vertex over there, and then it predicts an end face signal or next face signal that says, I'm done with this face. It's able to generate faces which don't have a fixed number of corners. It could have like 3, it could be a triangle, it could be a square, it could be an octagon. It could predict faces that have variable numbers of corners of vertices. And that's how the model generates an object. So at the end of the day, we've got something that's just predicted all the elements of an OBJ file, and then it's representing a mesh. Here are some examples. These are class conditional samples. So not only what we can also do is instead of just conditioning on the vertices that is generated, we can also condition on some like initial embedding of a class. We also can condition on an embedding of an image or of a 3-dimensional voxel diagram. So we can like say we want shapes that are all lamps, or we want shapes that are all sofas or clocks or cabinets or jars or benches or monitors or chairs or tables. And we just sort of embed these categories, and it's been trained to only predict vertices that would be consistent with those types of objects. And these are examples of like generated objects for each of the categories after it's been trained. And I'll show how it's actually this is actually generating stuff in practice. So you can see like first it'll generate all the vertices of these meshes. Not sure why the center one's not going. Okay. You can see all these vertices in the center are being generated. And then at some point it finishes, and then it goes into the face phase of its generation. It's building all the faces, and then it just built a couch. Here's how it works for the lamp. Vertices are all being generated, and then it generates the faces. And same, oops. And here's, I think, for this vase. And so they're pretty good. Charlie there's a bunch of different metrics that like the sort of geometry or like graphics communities use for like the goodness of a mesh and how faithfully it represents another mesh. And the scores, you can see that they're pretty good, so it scores quite well on these metrics. Okay, another project that's sort of similar and very, very similar in spirit, but applied to a different domain. And so instead of meshes represented by like OBJ files, you can have chemical graphs. Now the role of the vertex in the mesh is played by the atoms, and the role of the the edges that comprise a face in the mesh is played by the bonds. So a chemical graph is just another, here's another graph, and you got your nodes and edges, and you can play a similar game. So this is work by UGLE. It's a different model. This is actually, I think, before transformers really were. I think we did this work actually before transformers. If transformer was even out, we probably would have used it if it was there at the time. But here, it's a very similar idea. It's kind of like you can think about it as a generative model over chemical graphs. And each step, it's going to be predicted by a graph neural network. Is going to decide on each step. It's deciding like, do I add a new node? So now instead of doing vertices and then faces, it's going to interleave these. So it's going to say, I'm going to should I add a node? If no, then it's done generating that molecule. But usually it'll say yes. And then if I say yes, do I add an edge between this node and another node, like another atom in the graph? if it's no, then it just goes back, then it's done sort of connecting that atom to the bonds to other atoms, and it just goes back and decides whether it's going to add another atom. If it says, yes, I need to add another edge or another bond, then it picks which node to add the edge between the new node and the existing nodes. Similar thing, it's just almost like that, the one we just showed a minute ago, but interleaved, right? Every time it adds a vertex, it would like add another set of edges around it. And it's trained in a similar way to optimize the log likelihood of the structure. Here we do some like Monte Carlo integration over different permutations, and this isn't important though. But and this is a sort of little schematic on the bottom of how this works, and you can see it sort of building up some chemical graphs. And then here's some examples of our models generated chemical graphs. There's, I think, since this has been published, there's been more sophisticated models that have come out. I don't think this is like state of the art these days. But part of why I'm showing this is just to kind of, I was really trying to show how we take, like how we're sort of taking the same ideas and applying them to like kind of very different problems, and just to sort of communicate the sense of like that really when you just need to think about like what are the elements, what are the relations, and like what does the model need to learn about their interactions in order to like sort of make predictions of whatever you care about. Right, so again, on the left you have your training set of examples of molecules, and the far right you got our model, and then like one of the sort of state of the art at the time, this grammar VAE is sort of obviously worse molecules, but I think that they're in the actual scores. I don't think ours is state of the art these days. Cool. Okay, so let's see. I have about. Let me go through this quick, and then I'll leave time for some questions if that's okay. So the last bit of work is sort of related to a lot of these things. This is kind of intended to show how we've taken some of these like graph neural network kind of edge node and graph level prediction sort of things that we've done, or that they can do, and then kind of string them together into more complicated systems. So this is sort of motivated by this idea that like humans are a construction species. So we really feel that sort of like one of the most important sort of defining features of human intelligence is our ability to build things. We like as children, we like build, stack blocks. We love to like build different things out of paper, sandcastles. Like if you have kids, whenever you take them to the beach, they're just completely like immersed in, digging like the channels and the water. And I did it when I was a kid, and I know that all of you did it when you were a kid, because that's what kids do, right? And like, we build shelters in like the Arctic. We like build like amazing architecture in London. We're not even satisfied building stuff on Earth. We go into space and we build houses up there. Okay, so we're a construction species. So what we're trying to do is in this work was start to try to get a handle on how we can make agents that will build stuff. And this is a sort of very modest attempt, so don't get too excited when I show these kind of flashy images, but here is the sort of example of our domain. So the task is going to be pick up blocks that are under the floor and then place them in the scene by stacking them up. You can make them sticky if you want, but you're going to usually pay a cost for that. And the goal is to not touch the obstacles when you build you build your little structure, and then you're going to have some other so you're never allowed to touch the red things, these obstacles, and you also might have some other tasks, such as in the left column. This is called the silhouette task. Initially, on the top row, you're given this like kind of shadow, this like green shadow of where you're supposed to place your blocks, and then on the bottom you can see a successful construction. So these blocks that are these kind of blue and gray, cyan and gray, bluish gray blocks are the structure that has been sort of built by the agent. It gets 1 point if it met every time for any target block that it covers, and it pays 0.5 for making any block sticky. When it makes the block sticky, that's represented by these gray circles. That's like, it means that when it's sticky, it means that that's going to be a fixed attachment point. And so it can kind of build like more complex structures that would fall over by like anchoring them to the ground and things like that. Second column is our connecting task. So in the top row, you've got these little blue floating squares, and the agent's job is to stack up a structure that touches those squares. So it needs to arrange the blocks in such a way that it can touch the squares. And you can see again, it successfully touched all of those three blue squares at the top while avoiding the obstacles. And then the third and fourth column are kind of more interesting tasks. these are where the agent has to build little structures. So it's not just avoiding the red obstacles, it's going to protect them from the rain. Okay, so you can see it's going to build little houses or other like lean-tos and things like this over these red obstacles. The more it can cover up the red obstacle and prevent it from like kind of being exposed to rain from up above, it gets credit for that, and it pays some amount for making the blocks sticky. So it should try to avoid making it sticky unless it needs to. And what we did in this work is we actually there's a lot of sort of moving parts in this, but I'll sort of get to one of the key contrasts. We contrasted absolute versus relative action. So this is a little bit of like a kind of a label for a kind of broader distinction between some of these architectures. The absolute one, it takes a scene graph as an input. We have lots and lots of model variants I'm not going to get into, but this one, this distinction, it takes a scene graph as an input, like a bunch of objects in the scene. But then it just makes a graph level prediction about which object should be picked up off the bottom underneath the floor and where it should be placed in the scene. So it's not like really relational in any deep sense. It's like taking an input graph, but its job is to make a global graph level prediction about which block and where to place it. On the right, we have a relative action, or this relative agent, which we'll describe in a second, where it's basically taking a scene graph in, and now it's going to make a prediction of its action is going to be edge level. So it's going to be deciding, it's not going to be predicted like on the input graph, which connects. I probably should have showed this slide. Sorry, I probably should have showed this slide actually after the next slide. Now let me just go to the next slide and I'll explain it. I'll describe how the agent works and I'll go back to the slide. I haven't presented this in a while, so I probably got the order wrong. Okay, so anyway, so here's our agent. So basically, it makes an observation of the scene, and that's the left. So you got your red obstacle block, that's A. You got your B and C blocks. Those are like blocks that have already been placed on the floor. That's because they're above the floor black line. And then D is a block that hasn't been placed in the scene yet. This four objects these are represented as a graph shown here in the center. And the agent is going to make predictions. This edge-based relative agent is going to make predictions at the edge level. So it takes the input graph and then it outputs a graph where the attributes on the edges of the graph are going to indicate they're going to be it's sort of a competition. Whichever edge attribute is like the highest score, that's where it's going to place the block. So it's making like a relational sort of like edge level prediction. You can kind of think about this like Legos. It's going to be saying, I'm going to take this brick, I'm going to snap it to that brick, or like at least stick it, like rest it on top of that brick over there. So again, so we've got a graph neural network, and it's predicting. It's a deep Q network agent, sort of an old style of RL agent for deep RL. Is predicting a Q value. Is predicting at each edge level what is the predicted to be the most valuable edge to place this block on. So here in the schematic, you see it's placed the D block on the B block, and that's reflected in the graph. That white box in this kind of edge between D and B. That's like the highest scoring Q value, and that's the one that's going to determine where it places the block. The reason there's multiple values on each edge is it's, again, like Legos, you can place it at different locations on the edge. So in this plot, you can see I've got this little like kind of these hash marks that are meant to indicate different locations where it could place this block on this other block. Hopefully that's sort of clear. So anyway, so here's, yeah, there we go. So here's some agents doing each of the tasks. The absolute agent, we found a really big difference in most of the tasks on this absolute and this relative agent. So it's making these graph level predictions. It's not really exploiting the graph structure that much. It's usually making simple constructions, and it's just not getting that much as much reward. The relative agent is usually got quite a bit more reward. So this is the simplest silhouette task. Here's the connecting task where it's building little structures that need to reach the ceiling. You can see the absolute agent often just falls into these weird pathological behaviors too. We don't really know why, but like you kind of get some of them right, but like it really struggled to kind of just get reasonable sort of performance. The relative agent you can see is very effective. The different colors, when it makes the block sticky, it has a lighter shade of like bluish green. Okay, so the covering tasks, which are kind of more interesting. So here's this like covering task. You see the absolute agent sort of always makes these little like igloos over it. It always does that. I don't know why. The relative agents, again, makes much more sophisticated structures. This comes in handy when it's trying to get things that are like kind of not too close from each other. And then here's the covering hard task. The reason we called this covering hard, probably should call it covering like probably, I don't know, like limited resources. If you look on the bottom, it's only, and the other ones that could use the blocks, it's like with replacement, so it could use those blocks on the bottom as many times as it wants. Here it has it can only use them once. So it can only use these blocks once, which changes the whole story, because now it has to like, it really wants to use those big long blocks, but if it can only use them once, it has to like save them. Okay, so it really has to start thinking ahead and being like, when am I going to need that blue block? Because if I place it too early, then I can't use it at the end, the long block. Okay, so here's sort of like the general performance we were seeing. So on the x-axis of each of these plots, let me see, each column corresponds to a different task. You can see the task label at the top. Let's just look at the bottom row, because the top is like all the levels, even the easy ones. The bottom row is like the hardest levels, where like by metrics that we use to determine which ones are hard. So you can see the relative performance. The absolute is always the left light blue bar, and the relative agent is the dark blue bar. So for the silhouette, connecting, and covering tasks, you see there's pretty substantial difference in reward, which is the y-axis. The total, like the average reward that they're getting in the hard levels. The relative agent always gets like about twice the performance roughly. We don't see that pattern in this covering hard task. The problem with this covering hard task with the limited resources is like none of the agents were actually performing well. These scores, it's hard to normalize these scores. Like when you have different numbers of blocks and stuff, like the scores we had to kind of tune the tasks. So these scores are actually quite poor. The model free agent does okay, but it's not doing that great. The whole reason we had built this task with these limited resources was forcing the sort of late choices to depend on early choices, was we wanted to explore model-based agents. So here we actually built a second agent where now it's doing all of this sort of graph building, but in its head. It can try these things out in its head. So it can use MCTS, like Monte Carlo tree search, which is a search algorithm that's often applied to, most famously like Go and the AlphaGo system. But we can use MCTS as a general algorithm in this construction task as well. And we can use it with these graph neural networks that are going to be, making these sort of edge level predictions. And part of this was mostly just to demonstrate, it's like a proof of concept that we can start to build very complex sort of agent architectures with other techniques from other parts of the literature. But like with these sort of graph neural network relational prediction cores playing a sort of central role. So we built this, and again, it does MCTS to estimate the Q values instead of just learning a sort of Q prediction in a model-free way. And when you do that, you get better performance. So what I'm showing here in these plots, the orange is the performance I showed before. That's like the model-free agent. That's those orange circles. And then if I just to draw your attention to the dark purple is basically the model-based agent. It's both during training and test. And you can see in the covering hard task in particular, the model-based agent starts to do much better than the model-free agent now. And I should say this is also true for both the relative and the absolute action. Sorry. This is only true for the relative actions. In the absolute actions, there wasn't that much of an impact. So this is that relative action agents making the edge level predictions and using the search MCTS model-based planning. On the right, you have videos of the types of structures that it's able to build. It just failed on that one. But you can see it sort of choosing very carefully where and when to use as well. Okay, that's it for the talk. So, but yeah, the conclusions, I think, is quite simple. I mean, we can represent many complex systems, scenes, objects as graphs. GraphNets and transformers are able to be trained to make edge, node, and graph level predictions. The input graph, and then this means that this covers a very wide range of use cases that we can come up with, from construction to simulation to generative models of objects, molecules, and these models can also kind of interface within much broader deep learning systems, like using autoregressive sort of generative models or just big RL systems with search. And the last thing I just wanted to say too, I think I mentioned at the beginning, we've open sourced a lot 2 graph network libraries, both in JAX and TensorFlow. And so I'd encourage you to play with them, and if you want, and send feedback. We're always excited. I think I have a couple of slides just demonstrating this. It's quite simple. So Giraffe is our JAX one. We just released this about a year ago. it's quite easy to get off the ground and just start building these types of models, and they should work in lots of different sort of settings, and we have model and training examples. Same thing for the TensorFlow one, which we don't use as much anymore because we just don't use TensorFlow as much. But Google more generally uses TensorFlow, and they actually just released also a TensorFlow GNN library that's sort of taken some stuff from our GraphNets library, and we sort of collaborated with them on this. So if you're into TensorFlow, you can use that. And here's a bunch of other libraries that we did not build that are great, that other people in the community have built. That's it. Thank you very much. Oh, code. Sorry, code for my for some of these papers too. For most of the papers, I think we have released code, or at least for the environment. So if you're interested, you can check it out. Thanks.
Thanks, Pete, for this very inspiring talk. I guess we have a couple of minutes left for questions. So we can start with the questions from the chat, and then we can try to make it as interactive as possible. So if anyone has questions, just feel free to unmute yourself. So there is a question in the chat. How do you take care of different variations in the data, I guess? For example, clothes changing the orientation. That should be for the first part of the talk, I guess.
Yeah, here I try to get the. Let's see. The orientation. It's the model takes as input the positions of the nodes and the displacement vector between them, but like it sees, because it gets lots of data that is trained on, it sees lots of examples of like all the different orientations. So it does, like, it's sort of it's not going to be surprised by any orientation because it's seen most orientations before. I'm not sure if that's so. There's two things. One thing is like a lot of these models that I've described, they generalize well to, like, I didn't say this, but we often build them to be translation invariant. So we don't actually give the absolute positions of things. We give like the relative displacement between things. And even though it's going to be, the updater is going to update the absolute position, we sort of like don't give that to the model. And you can kind of set things up in a way that it's sort of trivial to do this, but that it's going to be never actually, the model's never going to actually see the absolute coordinates. And that way it's by construction translation invariant. Certain things like rotation is harder to do that for. So in the molecule sort of property prediction community right now, there's a whole bunch of interesting models like DimeNet, DimeNet++, a whole bunch of different things that people are exploring for building in different kinds of like rotational equivariances and things like this. We haven't really done that much with simulation. We played this a little bit. We haven't really used this that much. So I'm not sure if this sort of gets your question too, but like you can either build, there's two things you can do. You can either augment your data or at least maybe make your data dense enough that you see all the orientations or whatever type of variation you want it to handle, or you build in by construction an equivariance to it. Those are the two ways to sort of like, tackle the problem of like being able to generalize or handle those types of things. So should I just go to the next thing in the chat? Or?
Yeah, I guess we can. So there are two questions from Santiago.
Okay, I'll just read it out loud in case anyone's not an expert on fluid dynamics, but there are probably phase transitions on the dynamics, for example, laminar versus turbulent flow. Any comments on how this is learned by encoded in the graph network? Let's see. Yeah, so in this one, like in these kinds of settings, so you see in the water regime, for example, there is like, I don't know if you're really going to see vortex shedding or like the kind of like funky behaviors that like in complex turbulence here, but we and others are sort of exploring these types of things. We actually have a paper we just put on archive that's also under review on like much more complicated turbulence simulation models. I didn't talk about them here, but these aren't even actually used. These are just using CompNets we use because it already, the data comes as like a grid. Yeah, generally, I don't know. Like, I think I don't think that as long, okay, so these simulators often don't, okay, so many of these simulators don't know about, like, differences in phases. They're just modeling the physics at a very fine granularity, and then these are sort of like kind of there's higher level types of phenomena that can emerge from this, similar to how like people will implement very fine-grained molecular dynamics simulations and then use them to try to fold proteins. Like they're not putting folding or anything like that into the simulator. They're getting the simulation right at the very fine temporal and spatial resolution, and then but because they get it so accurate, it can it can do a good job of capturing the high-level sort of emergent phenomena accurately. So I'm not sure if this is what you're getting at, but like, yeah, anything that's it's just trying to learn a function, the different parts of what the simulator is doing and approximating that. And there's some failure modes too. Like I didn't really talk about this that much. There's not many, but like, and you can find certain regimes where it doesn't work that well. But yeah, like I'm not really sure.
Cool, thanks.
Okay, so then next question: what do you really gain by using your framework and simulating fluid flows compared to CFD models? Well, yeah, so I had said that at the beginning, like, why bother even doing this at all? Like, why bother learning simulators? So there's actually, I gave, I think, 2 reasons. I said, one is that you hope to strike better speed accuracy trade-offs. So that's one. Like, again, this simulator was 10 to 100 times faster than the ones it was trained on, so that's good. Another one is we're starting to train models on real data so that you don't even need a simulator. Other ones, there's other work, in some work we've been doing recently, we've also been, okay, so one thing is these models are all differentiable because they're neural networks, so you can train them by backpropagation. That also means you can backprop gradients not into the weights, but into the inputs. So if you want to do gradient-based optimization of, say, the shape of something to get it to behave in a particular way, you can do that. And we have work that's going on right now where we're doing that, and we're gonna, we haven't put it out yet, but you'll see it soon, hopefully. Other people have done some stuff in this space as well. There's not much, but I can point to this. I didn't put this paper in. There's actually a paper we had I think we were the first ones actually to this. In 2018, we did this with like Mujoko robotics simulations with similar class of models. Great, so we use gradient-based optimization like model predictive control to optimize control inputs for a robot controller. If your simulator is not differentiable, you can't do that. Another reason is because another thing we've been doing is we have a workshop paper on this where because these models have these like inductive biases for, like here, let me go back to this part. Like basically what we do is we take these edge functions, phi e, and because they like correspond to something physically meaningful, which is like the interactions between things, which in classical mechanics would be the forces, we can actually we can train the model on real data or on simulated data, but real data is where it gets exciting. Actually, simulated data is exciting too, for a reason I'll say in a second, but train the model on some data and train this phi e in the whole neural network, and then you rip out the phi e and you do symbolic regression on it. So we've been doing this in these orbital dynamics systems, and what we do there is we do symbolic regression on just that phi e function, and then that lets us fit an equation to the force law, and it turns out we can get Newton's law of gravity correctly out of this. So basically, what we've done is I have slides on this. I could actually pull them up if anyone's interested later, but we get like Newton's force law just from the raw data of observing solar system, like the trajectories of the moons and planets and sun in the solar system. So that's kind of interesting, and you can even do this with simulators. So we have a paper from NeurIPS last year, like 2020, where we're learning like kind of symbolic expressions for relationships within these sort of complex dark matter simulations. This is a collaboration with some astrophysicists from Flatiron Institute, and there, no one really knows. Like the simulator is simulating a fine granularity, but we don't really have equations of like kind of effective or like equations for all the phenomena that are like all the relationships between the different parts of the system, and you can sort of get that out as well using symbolic regression. So basically, it's a little bit hard to explain. I kind of have to give out like a longer detailed thing, but the basic story is you use the neural network as a stepping stone. It has certain inductive biases that you can train it at large scale on real or simulated data, and then you take it apart and do symbolic regression on the key parts that you're interested in. And I don't really know how that would work with like a real simulator. So those are some reasons why you want to learn simulation. But for fluids in general, I think just efficiency is really where you're going. Oh yeah, is it possible to use your models to control the behavior of fluid flows? Yeah, just there's one paper called it was 2019 or 18. I forget the paper's title. It was Lee was the first author. Josh Tenenbaum, Russ Tedrake were on it. And they were like controlling these little, they weren't really fluids, but they were kind of these like non-rigid things. We've got some, I think we're going to put probably out within a month or two a paper where we're really doing a much more sort of like involved version of this. It's very similar to what I'm showing, except instead of like it's taking another step. Instead of just predicting what's going to happen, it's then predicting, or it's like controlling or deciding on a surface that will cause something desired to happen. Actually, I can't really explain much more now. It's easier to just wait for a month or two.
There is actually another question, but it was sent as a direct message to me. So, hi, Dorina, could you please ask the speaker if any work has been done or will be looking into the digital healthcare?
Can you say that again? The what healthcare?
If there is any work that has been done or will be looking into for digital healthcare.
Digital healthcare. Not from my group. Actually, Doreen is a better person to ask about this. No, but we haven't. No, but I mean, I think an interesting question. I mean, okay, there's different things, right? So this is not anything that I'm an expert in, but I'll just say that like graph neural networks in general, like geometric deep learning, graph representation learning, is often used to for knowledge base, for knowledge graphs, and different for example, there's like the OGB, the Open Graph Benchmark, is a big, nice data set of graph problems that's been organized by Yuri Leshevik at Stanford and collaborators. In some of those problems, you have things like the archive graphs, like citation networks, like who's citing who. This is sort of like closely related to knowledge graph problems. I think that I'm not quite sure what the detail, what the question is referring to exactly, but I mean, again, my group doesn't really do this that much, but there are definitely people who are applying graph neural network, graph representation learning to, networks of sort of complex relational databases and things like this. If there's a specific problem you have, feel free to email me and I can point you to someone who knows about it or try to.
There is a last, well, I don't know if it's the last, but there is another question on how do you generate the training data set for fluids, discretized Navier-Stokes?
Yeah, so there's different, yes, broadly speaking, yes, we have different simulators. I think I mentioned there's in fluid, I'm not a real expert. The key person is my collaborator, Toby Pfaff, who's he did his PhD actually in the sort of physical simulation, complex materials. So he's a good person to ask. But basically, yes, SPH, smooth particle hydrodynamics, is a Lagrange method for discretizing and sort of numerically integrating the Navier-Stokes equations. The material point method we use. Some of these are more SPH is sort of very general. MPM is I think a more graphics kind of specific simulation tool. We use a lot of different simulators, but basically, yes, broadly speaking, the Navier-Stokes equations for fluids are approximated and numerically integrated in many different ways and different techniques, and whatever the underlying simulator is that does this, we just take its we're sort of a little bit downstream from that. We're like, okay, we assume it did something, and then we take the kind of representations, particles, meshes, whatever, and then just do the learning there. But broadly speaking, yes, they all do.
Okay.
That's what the question's asking, if I understood it correctly.
Maybe any last question from the people connected? Maybe I can finish with a question if there is nothing else. So I was wondering, you mentioned in the end, you concluded your talk with this type of blocks, etc. So have you tried to include this notion of blocks into the generative process of your previous parts? So if I understood correctly, while, for example, in the chair, while you generate the chair, you go point by point, but is there a way to take into account some block structure in order to generate parts and not necessarily go into a point by point generator?
Yeah, that's a good question. So we don't do that really. We would like to, but we think it's really hard and we don't really know how. So here's the problem I see. Like, as soon as you want, okay, actually here, let me show an example. So probably the closest thing is this, this box bath thing where you got the box floating around in the fluid. Not because that box is like a kind of more abstract general part, but because it was sort of hard to get this to work. Like getting the cube to not dissolve and sort of fall apart, like to keep its relative shape is sort of hard over the simulation. Like it takes sort of like some, kind of clever, like we have like a lot of kind of like noise regularization sort of schemes that we talk about sort of in like the appendices of papers mostly. But like those do sort of like make kind of a difference. The reason I'm bringing that up though is because like parts, okay, so there's two things about parts. One thing is that they're complex. I don't even really know how to represent a part. It's like more complex than like sort of some kind of like geom, geom primitive. Like how do you represent an ear, or like just what is the representation of that if not for like a mesh, or right, like what's a vector? Like right now our nodes in the graph are like always represented by vectors, which they don't need to be. You could have some kind of other thing, a set or something. But I just don't know how to represent like a ear or a nose as like a vector, really. And like in such a way that then you could also, the reason I brought the box is like then you also want to stick the ears like exactly touching the head, the nose exactly touching the face. So yeah, I think it's the way to go. Like I think it's a really important question, and we've looked a little bit at like coarsened models and hierarchical models for these sorts of things. We have a paper with Kim Stackenfeld from last year. This is a little bit different, but it's like spectral graph networks, where basically we have this sort of like low-level graph neural network and then a high-level kind of spectral representation of the thing, and there's like kind of bipartite connections between them. But we didn't apply that to any of these physical settings that we should. It's just, I'm not sure. I think it's a great question. I just don't know how to do it. Like, yeah.
So if there is no other question, well, Pete, thanks a lot for this very, very interesting talk.
Cool. And I can, I was gonna say I could share a PDF of the slides if anybody's interested too.
Yes, please. I mean, so there will be a recording available online in the website of the seminars. And yeah, it would be great to have the slides as well available, if you're okay with that.
All right.
So
thanks
a lot. Thanks a lot. And thanks everyone for attending. So the next talk will be in 2 weeks from now, I think, from Michael Bronstein. Yeah. Have a nice afternoon, evening, morning, depending on where you are. And yeah, thanks again, Pete. Bye.
Thanks.